Right, let's get started. So I want to ask you one question first. Are you all comfortable with LT Spice? You do? There? Right? You haven't done that in the past, right? So did you take, so who did you take the circuit one from? Where? Who? Some college, that's why. Okay, never mind. So if you have any questions regarding LT Spice, let me know. I think I recorded a series of tutorials. You saw them, okay. Oh, logic. Great. Perfect. Okay. So do we have a quiz next week? When? Wednesday? Do we have a homework due on Wednesday as well? Yes. Since we have a homework due on Wednesdays, then I'm assuming you guys have been trained on how to calculate that R2R DAC ladder. Yeah, prepare for it. So the scope for building that ADC is called SAR ADC. I'm going to introduce that structure today. But the scope of working on that SAR ADC for the first half of the semester will be only simulations for the SAR logic, SAR, which means successive register approximation analog to digital converter. And eventually there will be a course project. And here's a sample of the course project. Was done by another student who worked with me in the past summer. And we actually designed every single component in the SAR ADC, and it worked. So it's not an ideal ADC anymore, like the ones you are going to simulate in the lab next week. With something you can convert into an IC chip. And that's what we are doing for the senior SUM team this semester and next semester to really tape it out. Tape, T-A-P-E, out. That's a term used for the IC industry. Tape out can be tape dash out. It's a noun. So you're having tape outs, which means you are fabricating chips and with any of the foundries. Or you can say you are taping out any IC chips. Because eventually, whenever the chips are done, they just put the tape on the chip, or they just peel it off, whatever. So there's a clean room tape on the chip. That's probably where that came from. And so the course project for this class there won't be any fabrication involved. So it's literally just LT Spice simulation, and it's a lot of work. If you look at this one, it's like 19 pages report, and I'm expecting you guys are getting something similar as a course project to understand every single component of the ADC. Very useful, right? So starting from building these buffers, that's a buffer, and that's a NAND gate, and that's a D flip-flop. It's actually being sold by TI. It's a same structure as a Texas Instrument TI can buy on the market. The same schematic. So we're going to go through the theory behind this as well. So it's a set and reset D flip-flop. As a block, a schematic of that D flip-flop, and that's a sample and hold circuit. Oh, is it? Oh, it's a comparator? No, it's not a comparator. It's a sample and hold. That's a sample and hold circuit. And that's a SAR logic block. You have to verify every single bit from the output. You have to design a timing. That's a DAC. And that's a simulated output. As a comparator, we may want to use a different structure because this comparator is not real to real. RAL, real to real. Bottom real, top real means ground and power. That's another term you want to say in electrical engineering. So real to real means the input swing can reach both levels, both two rails. There might be some threshold drop on the top and not the bottom. If you have a better design, the input swing can reach to the top rail and bottom rail, or even pretty close to the two voltages, which is a good parameter, right? It's good to have rail-to-rail swing. It's analog swing, right? It's analog input is swinging around one base point, and you have power supply, VDD, and ground. And if you have a design like this one, it's not rail-to-rail, which means whenever the swing is getting closer to the top, like 5 volts power, it's going to be cut on the top. So you do want a rail-to-rail swing. So there is another design we can consider, right? As a comparator is actually an OpAmp, but nothing else. And timing logic is literally the counter. Like you're controlling, like whenever you want the data to be to be sent out to the output. Counters, timing logic, and that's the final schematic of everything. And it's sampling like this, so you can see compared to the ideal one, it's not doing really well. But this is something you can fabricate. Right? That's the real world stuff. Okay. So just let you know what you want to expect for the course project of this class. So let's get into the topics of this lecture. First, here's an example regarding DAC. The question is, find the number of input combinations voltage values for one LSB. What does LSB mean? Let's just stick to bit, right? One LSB. And full scale voltage generated for a 3-bit, 8-bit, and a 16-bit DAC. So VREF for this case is 5 volts. So you need to list everything in the table for this problem. So before we start writing down anything, you want to see like what this problem is asking you to do. Right? The number of input combinations. I can imagine that the DAC is a block like this, right? So there are many inputs. Depends on the resolution of the DAC. And there's a VREF. So whenever people ask you regarding the resolution of the DAC, so what do you want to say? For example, you're designing a system, you tell someone interviewing you when you are trying to find a job in the company, and they ask you, you tell them like you have used some kind of ADC or DACs for a system, right? They will ask, so what's the resolution of the ADC or DAC? What you want to say? High resolution. What's the answer for that question? What's the resolution for that DAC? 8-bit, 10-bit, 12-bit, right? Not 12 bits, right? 12. It's a 12-bit ADC, or the ADC is 12-bit, or it has 12 bits for the input. So the resolution for these three types of DACs are 3-bit, 8-bit, and 16-bit. That's a table. That's the 3 entries. And input combinations, the number of input combinations. How many? For the 3-bit DAC, how many different possible inputs it may have? 8, right? 2 to the 3rd. This one is 2 to the 8th. What is that? If you have a lot of experience with building this digital system, you should get this answer instantly, right? 256, right? And so what about 2 to the 10th? 1024. Okay. So what is this? 256. This. 65536. So nobody will expect you to answer that question, right? Up to 10, I guess. I mean, reasonable. So what about 2 to the 20th? It's actually easy. So 2 to the 10th is what? Remember in digital, I don't know if I covered that, but 2 to the 10th is 1024. It's also called 1 what? 1K. So 1 byte is 8 bits. It's only 8. This is 1K. It's not 1,000 literally, but it's 1K. It's different concept. Sometimes people will equalize 1K to 1,000, but depends on what kind of context you are talking about. But I think in digital, 1K is not really 1,000. But a lot of situations, they will say it's just 1,000. This is very close to 1,000. But you'll never get 1,000 in digital system, right? It's just 1K. Physically, there will be 1K spots or memory bits in there. So what about 2 to the 20th? So it's literally 1024 times 1024, right? 1 million. 1 mega is not 1 million. It's 1 mega. So what about, wait, is that correct? Yeah, that's correct. So what is 1 billion? Is that 1 billion? 1,000 of 1 mega, it should be 1 billion. It's actually not 1 billion. We don't use billion here. What we use? Giga, 1G. Yeah. It also applies to LT Spice, I guess. If you put a G there, they are going to treat this one as 1 gigahertz. Okay. 1 LSB. What is 1 LSB? Voltage. So we know it's 5 volts for the VREF. And so what's 1 LSB? So you have this type of resolution, which means there will be 8 stages to divide that 5 volts. So it's actually splitting that 5 volts into 8 pieces. So anything lower than that cannot be resolved. So that's the resolution. It's a poor resolution. 3-bit is very poor resolution, right? So there are only 8 steps to split that 5 volts. So 1 LSB is going to be 5 volts over 2 to the 3rd, which is 5 over 8, which is what? That's 0.625 volts. That's every single step. Anything lower than that cannot be resolved. That's the sensitivity of this ADC or DAC. for this one, it's 5 volts over 2 to the 8th, which is 5 volts over 256. And I don't know the answer. 5 volts over 2 to the 16th, which is 5 volts over 65536. And there will be a pretty small number for the 16-bit. I can see it is able to sense a very tiny voltage change or output very little tiny steps for this input. If you have 16 lines for the input, the resolution is pretty high. So there will be one sensor, so the highest resolution I have ever seen in my life as an ADC. It's called HX7011, and that's the ADC for string gauge. And you can directly buy the module like $1 for each. Is pretty easy. And it's 24-bit resolution ADC. Because it's being used to sense a little tiny resistance change of the string gauge, amplify it. So it has to be very sensitive for the application. And I've used another ADC which is being used as embedded inside a capacitance to digital converter, CDC. It's a chip being sold by ADC, the company, 8 Analog Device. That company is pretty famous, and LT-Spice has been acquired by this company. It's probably the biggest company making ADCs on this planet. So they acquired linear technology, which is also a semiconductor manufacturer making so it's called LT741, like all these devices you have seen in the lab. LT means linear technology, and that's what the LT means, is linear technology. That's the company's name. So LT-Spice. So Spice is everywhere. Spice means something like you can use in the kitchen, and it's short for simulation program for integrated surface emphasis. And the reason I can remember that is because in my graduate school, the professor put that on the final exam, and I hate that a lot. But I memorized it anyway because of that. So Spice is a general purpose software, like allows you guys to code it up, like what you did in the lab. So R, from node here to there and whatever, right? So you can put a simulation to there as well. So LT-Spice is one of the spices, and there's a P-Spice. It's just from different companies, but they use the same core, same concept. You can do it all the time. And H-Spice, N-Spice, which is the worst, and all different types of spice. So LT-Spice is free. It's been popular recently because it's free and being maintained by AD, this company. So that's why I highly recommend just using this for some like regular simulations. But in the future, for professional simulations, you have to use either H-Spice or there's another one called Spectra embedded in Cadence. So you guys will have a chance to use that one as well. So P-Spice is from the company who, that's the same company who maintained Altium. No, probably not. I forgot. So it's not free. So you don't have to use P-Spice. So LT-Spice is good enough for this class, right? LT-Spice is from Linear Technology and acquired by AD. Right? LT-Spice, LT belongs to AD right now. All right, just happened a couple years ago, a long time ago. And the last column, the full scale voltage, V full scale. Remember the equation? Never put VREF there. It's a common mistake. So V full scale, which is the full scale output. What's the possible highest output it's able to offer? For 3-bit, what is that? So in general, it is 2 to the n minus 1 over 2 to the n times VREF. So for this guy, it's going to be 7 over A times 5 volts, right? And for this one will be, no, 7, sorry. Is that 7? Yeah, 7. 7, yeah, this minus 1, right? So for this one will be 255 over 256. Yes. But no, wait. Oh, sorry. Yeah. Yeah. Thanks. All right. Okay. All this. It'll be 65535 over 65536 times 5 volts. Okay. That's the first example. Sorry for the shade. Something control. All right. Move to the next. I have to go through some of the basics of the OpAmps first. You have learned OpAmps in Circuit 1, did you? Have you? A little bit? Circuit Electric Networks 1? And you have forgotten everything? It can be very confusing. Because we are going to use OpAmp for the ADC, and so we want to know how that works, but not the details. We cannot directly jump into it because it's going to be like very painful if you don't know what's going on, right? So first, if I draw an OpAmp, this is nothing but a 3-terminal device, definitely with power supply, but usually I don't draw it. And this device, don't think about too complicated. Okay, for this device, it's nothing but just amplifier, and it amplifies. If this is VPVM, this is VL. It amplifies the difference between these two inputs, and the gain is huge usually. So VL equals to VP minus VM, and times what? Times the gain. It's usually labeled as A, right? AOP. It's an open loop gain. Why is open loop? Because there's no feedback. We are learning the properties of this symbol, not everything inside. So I know you have questions like why is amplifying this, right? It's designed to do that. Right? You'll learn probably, I mean, I don't know, you probably will learn how to design OpAmp in the future, but now just memorize that. It's going to amplify the difference between these two terminals. And keep in mind, it's always VP minus VM times the gain, not VM minus VP. It's VP minus VM. So P is called the non-inverting terminal of the OpAmp. So OpAmp means operational amplifiers. For short, is OpAmp. The open loop gain is huge, like 1 million or something. Okay, so you are wondering, I only have 9 volts power supply, and I got like 2 volts and 1 volt here. What's the VL will be? Like 1 million volts. Is that possible? It's gonna burn the building down. But I have a 9 volts as a top rail, so it's gonna saturate. So what's gonna happen is you will see something like, if this is if VPVM works like that, right? So the input will saturate, so it's going to directly go to 9 volts. You won't be able to see anything higher than that. If you have that high voltage supply and also everything can handle that high voltage supply, it is able to go up to 1 million, but you don't have that. So it's going to saturate, be flat. So so the result is actually is comparing these two inputs. Why? Because if you do not have a feedback, it's running open loop as an open loop configuration. If you have this one larger than this one, it's going to output a 1. Vice versa. If you have this is 2 volts, this is 1 volt. So this becomes like 1 volt minus 2 volt times A, which is minus 1 volt times A. And you do not have minus 1 here. The lowest is 0 volts. So you're actually getting 0. It's going to be this. Let's compare these two inputs. Depends on which is higher. If you get VP is higher, boom, 1. It's like a digital output. If this is high, if the inverting is higher, boom, it's a 0. As the lowest it is able to reach, as the highest it is able to reach, because this is our two rails, top rail, bottom rail. However, if you connect the bottom rail not to ground but to like negative 9 volts, and you are going to get this kind of type of swing. Depends on the input, right? Is that possible you are getting something like intermediate voltages, not just directly shoots to the highest voltages or lowest voltages? Is that possible? Like some voltages are just staying in the middle? The difference has to be tiny, right? Like microvolts or something. But usually that won't happen because the noises are even higher than that. You know, it's difficult to maintain that small change. And we're not using this amplifier for that purpose. We're using this one as a comparator. So usually the difference will be big enough, even though a few microvolts or millivolts is big enough to trigger that jump. You know, it's going to be totally output, digital output. So this type of configuration is called comparator. It directly just leverages a function of the open loop configuration. So if I draw a input output diagram on the next page, so for this configuration, if I connect this one to 2.5 volts, and this one like is swinging like this, and I have 5 volts and 0 volts V out. So 2.5 volts is the reference voltage. This is 5. It's 2.5. And input swing from 0 to 5. I'm going to let you draw the output on this same diagram. So what the output looks like. So this is VP. This is VM. And this open loop configuration is just comparing these two inputs all the time and responding with a digital output. So when VP, for this time frame, VP is always lower than 2.5. So what the output should look like. So you are supposed to draw that output, right? And so when VP is growing, but still lower than 2.5, why 2.5? Because 2.5 is VM. And this amplifier is going to compare these two inputs and amplify the difference like crazy. But within that range. So for this time frame, it's going to be 0. Is that true? Because if you do a subtraction from from VP minus VM, so VP, the black line, is always lower than 2.5. So you're always getting a positive number. And that positive number, whatever it is, it's actually pretty large here. But even though it's very close to this 2.5 line, times a million is still a huge voltage. So it's going to saturate. And negative huge. It's pretty negative, very negative. But the lowest value is 0, so it's going to be 0. And after that, when this voltage, when the VP is a little bit larger than VM, to trigger that change, and boom. And for this period, it's always larger than VM, so keep high, and then fall back to 0 because whatever here is always lower than VM, then V high, V low, V high, V low, like that. Make sense? Okay, good. That's comparator. What's it?
I have a question on the, so when you're talking comparator, does it matter what our VP and VM are then? It's always going to saturate whatever your input voltage is, or does it matter what VM and VP are?
VM and VP are from the sensor. Depends on the purpose of the circuit, it's all different, right? So that you are getting different inputs. So based on that different inputs, you want to consider what you want to put in here for design, if that works.
Previous.
Yeah. So that's open loop configuration, but if you want to just amplify the signal with all the continuous different gains, you want to use a closed loop configuration, which I'm going to introduce after this. Okay. So it seems like this is really, just amplify to the top and bottom rails. It seems like not really useful. So if you want to amplify the signal continuously, you want to use a closed loop configuration. So it looks different. Yeah. This is just one value because you only have two static voltages, so you directly saturate this one to 9 volts. So it's constant 9 volts. You're not changing anything here. But for this one, you can see this is not changing, but this one is changing. So that's why you are getting a on and off digital voltage. And for closed loop configuration, first, inverting topology. So it looks like this. That's V in, R1, RF is feedback resistor, VL. That's called inverting topology because the input is being injected into the inverting terminal. And the voltage gain of this guy is VI or V in times RF over R1 minus. So it has a 90-degree or a 180-degree phase shift. So the question is, why this is not amplifying the difference for millions of times, but why it's like only, this is the gain, right? Because V in times the gain is VL. So now the gain is not millions, the gain is like RF over R1. If you have this one to be 10K, this one to be 1K, the gain is 10. It's not a million anymore because of the feedback. And the reason it causes this is whenever you have a feedback, it's forcing these two terminals to be the same voltage, even though they are not physically shorted to each other, but they are considered as equal. So 0 volts here, 0 volts here. And that's the starting point of getting this gain, finite gain, because this equals to this. And how do we understand that? If the professor doesn't explain this to you in circuit 1, they're going to confuse with this one for a whole life. That's what happened to me for a long time, until I designed one OpAmp by myself. Oh, that's why. A lot of people, even professors, are confused on that, and they're trying to explain to you guys anyway, but it's very confusing. So these two are equal. How to understand that? So first, one question, one interview question. So VP equals to VM. So that's VM, that's VP. Keep in mind, this is VIN, this is not VM. They have different voltages because of the resistor. That reasonable? They're not the same node. So VM, VP are always a wire directly shorted to the terminal, not something else, right? So this is VM, this is VP, always labeled that very close to the terminals. So think about that. Because of the infinite gain of the open loop gain of this guy, it is still amplifying that difference. So VP minus VM, if this VP is a little bit larger than VM, what's going to happen? So this OpAmp is still the OpAmp, still amplifying like millions of times of the difference of two terminals. And now VIN is not VM anymore, keep in mind. VIN is here. And we are talking about the voltage gain, which is VIN and VL, not VM, not the difference between these two and VL. Okay, so these are considered as equal because of the feedback, and has to be negative feedback. And now let's think about this intuitively. So if VP, so this is still valid, right? So if VP is slightly larger than VM, what's going to happen? So we're getting a little bit positive number over here, right? Like a little plus something times A. So the gain is the gain, right? It's going to amplify this positive number like crazy. So we're getting a huge positive number. So the huge positive number is going to do what? So you're comparing these two terminals. This is higher than this, a little bit higher than this. You are getting a pretty huge positive voltage here. And just happening very shortly, for example. You can imagine that. And remember previously, this is a little bit negative. It's going to dump current into this point and to force these two points to be equal. Because of the feedback, and has to be negative feedback, even though this guy is trying to be a little bit larger than this, it won't happen because it's going to feed it back. Whenever it's a little bit larger than that, electrons are moving at the speed of the light. It's going to adjust it to make them equal all the time. The same concept. If this is higher than this one, you are getting a little bit negative number here. It's going to be amplified to a super negative value, right? It's going to happen quickly, and then it's going to draw current from here and to force them to be equal again. So that's the magic of feedback. So you can never do anything wrong because it's trying to adjust them to be equal. And it's happening quickly because of the huge open loop gain. You have a small open loop gain, it won't happen that quickly, right? There's a little difference. Let's take some time to adjust it because the gain is low. It takes time. If the gain is huge, any difference, done. That's how I understand it. So these two terminals, as long as the legit OpAmp is not failing, it's going to have a huge open loop gain. Open loop gain, keep in mind. That open loop gain plus that negative feedback, it's going to force these two terminals to be a very close voltage values. You can consider this as the same voltages. So I'm going to draw another schematic here. So for non-inverting topology, for example, I just drawing another circuit here. So why is not the schematic is not being drawn like this? Anyway, whatever. So why is being designed like this but not like this? So never positive feedback, correct. It's feeding back to the non-inverting terminal, and it's positive feedback. Never do not positive feedback in electrical engineering. It's like something is doing something wrong and you are encouraging that person to commit more crimes. So you need a negative feedback. You do something wrong, punish it. Keep in mind, never positive feedback in any circuits. Keep in mind, never. So always do negative feedback for OpAmps. So how to derive the voltage gain for this one? Why it is this, right? So the way to do that is, also one thing you need to know for OpAmps, there's no current flow into the OpAmps. That's pretty interesting. We don't want to just derive everything and draw the circuits for you guys, but memorize it right now. So the currents are not being injected into the OpAmps. There's a, if you want to think about that, it's literally the gate of the transistors, and there's a dielectric material, so it's not directly dumping current inside. So all the terminals are inputs of the transistors, they are gates. So currents are not flowing inside the OpAmps. This is something like you want to memorize. Okay, keep in mind. So the current actually flows in that way. I mean currents. Okay. So here's 0 volts, and here's V in. So V in minus 0 volts divided by R1. That's the Ohm's law, right? So the voltage difference between these two terminals, and divided by R1, you're getting a current in this branch. Why is it 0 volts? Because this is 0 volts. The negative feedback is forcing these two terminals to be the same. So that's why I know this must be something very close to 0 volts. So is this grounded? So this is grounded, this is 0 volts. Is this one also grounded? So virtually is, but actually it's not. That's something you want to know. It's important. So it's 0 volts, but it's not ground. Very interesting, right? So just use 0 volts here for the calculation. V in minus 0 over R1 equals to 0 volts minus, since current is not flowing in here, so it's, you can consider this as the same current flow. So the current here is going to be the same current here as well. So you are doing 0 volts minus VL over RF. And just move things around, you're getting RF over R1 equals to minus VL over V in. Or you can say VL over V in, which is the voltage gain, which is negative RF over R1. So that's the voltage gain of this closed loop configuration. So a few things you want to keep in mind always for this calculation. First, you need a negative feedback. Always. Second, these two terminals are virtually shorted to each other. Virtually, not physically. If physically shorted, then this will be ground as well. But actually it's not. It's just 0 volts, but it's not grounded. Okay, don't dig too deep into that. It takes like a few lectures. So it's not an analog class, right? Just keep in mind. They are equal because of the negative feedback and the huge open loop gain. It's not always virtually shorted to the ground, because this is not always ground. If you have a little DC offside here, like 2.5 volts, what's the voltage here will be? 2.5. They're always equal to each other. Remember the negative feedback? It's going to force these two terminals to be the same voltage. Okay? Another configuration. I know this is boring because someone just let you memorize something and not understanding all the details is boring and annoying. I understand that. I was a student not a long time ago, and it just takes like weeks to cover everything. And if you want to pursue analog digital design, analog circuit design, you can go to graduate school. There are several other analog classes following up. The analog electronics you are going to take, which is Engineering 337, is the first one, and there is another one called analog IC design, and then advanced analog IC design, and microelectronics, RF design, mixed signal design. All these different graduate level courses you can take, so you can design a OpAmp by yourself. Then you can understand why it happens like that, all the details of the transistors. It's impossible to get into that for just like the undergraduate level. right? In engineering 337, you might be able to get into some of the OpAmp design details a little bit. But sometimes it's just frustrating. You just have to memorize it, understand that totally. Yeah. Non-inverting terminal, non-inverting topology. Is Vin directly connected to the non-inverting terminal, and here's V out. How do we want to feed it back? Warning, right? Always negative feedback. So there's nothing can be fed back to the non-inverting terminal, keep in mind. Never. The RF, using another resistor to form the gain, sorry, the R1. That's a non-inverting topology. So any mistakes you can make, but never make that mistake, which is like positive feedback. Never do that mistake. So if you memorize that, then you're always trying to connect the feedback resistor to the inverting pin, right? So for this one, the voltage gain looks a little bit different because you have to derive it in a different way. Because of the negative feedback and the huge open loop gain, you're getting what? Where do you want to get started? So I'm going to repeat this for many times for you guys, so you guys can explain this in the same way as what I do, okay? So because of the negative feedback and the huge open loop gain, so what's going to happen for this circuit? First, we're trying to derive the voltage gain. So what we are doing here, is we are trying to design a amplifier to amplify what? Voltages. Why do you need to amplify voltages? Because some of the voltages are tiny from the sensors, like millivolts, and you want to fit that range into your ADC. So for example, your ADC is like Vref equals to 5 volts and ground, right? You can resolve this entire range. You can resolve the entire range for the ADC. It's like an input for the ADC. And your swing of the analog signal is like this. You are wasting all the ranges. So your little step is probably the full range of the input. So you cannot resolve anything. It's always giving you a 1 LSB. And you are trying to sense something, but you are getting nothing. So you want to amplify this guy into this full range, right? So you can resolve it step by step. So you can sense it, sense the changes. That making sense? That's why you need amplifiers to amplify the voltages. So why amplify voltages, not amplify temperature? Because the sensor is going to convert temperature into voltages. Yeah, you cannot amplify temperature. How to amplify temperature? Use the AC. Turn the AC. Turn the HVAC. No, it's not going to happen in that way. So we need a. So I think that's a revolution because people find out electricity and about 100 years, maybe 200, I don't know how long time ago, and then people start thinking about using electricity to work in their everyday life. For example, you can design sensors to sense that temperature change and convert it into voltage. After it's been converted into voltages, electrical engineers will work after that. Will work into that block, including manipulate that voltage, digitize it, use the ADC, and do a data analysis. But first, you need an ADC and amplifier. So the amplifier usually put in the very front end, so directly interface with the environmental parameters, like can be anything, like light intensity, temperature, humidity, acceleration, angle change, anything, any analog environment signals can be converted into voltages. And sometimes you can have a current amplifier because some of the environmental signals are currents instead of voltages. This can be confusing as well because sometimes they're thinking like voltage and current, what's the difference? Why the signal is current, not voltage? Okay, so for example, the light, this is the photodiode, right? So for example, I'm going to draw this, right? So this is LED, and this is a photodiode. What's the difference? LED and photodiode, they are all diodes. But there might be some like different doping materials into the manufacturing process, but they are literally just diodes. If you give a plus minus voltage difference, it's going to shine light. It's LED. If you give a plus minus, it won't conduct any current because it's being reverse biased. And what's going to happen is whenever it's receiving light, it's going to conduct current in that way. It has to be triggered by lights. And LED and photodiode must be different in materials, but they are similar, but just for the details of the materials during the manufacturing process. However, a photodiode, you just reverse bias it, even though there's no current flowing through that statically, but whenever it receives lights, it's going to flow a little bit of current in that way because we have that reverse bias. It's pumping the current, but from top to bottom, and that photocurrent, it's called photocurrent, is proportional to the light intensity. That's how you can sense light. So here's the current. You have to use a current amplifier. This is not a voltage signal, it's a current signal. You have to use a current amplifier to amplify it and convert it into voltage. Keep in mind, always, you have to convert everything into voltage before you get into ADC. Why? Because ADC only receives voltage signals. So whatever in the environment, you have to convert it into a voltage. If you need to amplify it, amplify it. Okay? And then ADC. You got a digital signal, everything becomes easier. USB computer is just showing up on the computer. How do you derive this guy? We know V in here, and because of the open loop gain and huge open loop gain and also the negative feedback, it's going to force this two terminals to be the same voltage. So I'm getting V in here as well. And then, because the current is not flowing into the OpAmp, it's not going inside, right? So the current, you can imagine, is just flowing like this. And then V out, here's the voltage here, here's the voltage here, you are all both given. So V out minus V in over RF, the current in this branch is directly flowing down to the ground. So this is equals to what? V in minus 0, V in minus 0, V in minus 0 over R1. That's how I derive it. And then move the R's around, so we're getting RF over R1 equals to V out minus V in over V in, which is V out over V in minus 1. Or I can say the voltage gain for this non-inverting topology is V out over V in equals to 1 plus RF over R1. And there's no negative sign. There's no negative sign. Where do we have a negative sign? For the inverting topology, you got a negative sign. So there's a phase shift. If you don't want a phase shift, you want the input and output right in phase. You need a non-inverting topology. There's no negative sign. It's not inverting it. How can I understand it's inverting it? So if you're amplifying the signal as the input, so your output looks like this. As the inverting topology is going to amplify like that if the gain is 1. So usually the gain is higher, if you're amplifying, it's going to look like this, right? So if the input and output are in phase, are right in phase, what's going to happen is they are just being amplified, but there's no phase shift, right? It's input, and that's output. Pick, pick. Bottom, pick, bottom, pick. Okay? And they are all just drawing on the pictures. But when you are working in the lab, we don't have so they are being covering analog electronics for the lab. There are a lot of other things you need to consider as well. So I have a very important lab when I taught it. So like this thing, and there are all different configurations for amplifiers, and you need to set up a little DC offside and how you amplify, how filtered out the high frequency signals. And eventually, students were able to design a little heartbeat sensor detector because we used a oximeter. So this is an IR sensor, and it is able to. So you push your finger on the top of the sensor, so it is able to shoot IR light and reflect that IR light back to the sensor, and your blood flow contains oxygen inside. So that oxygen concentration is going to affect the received signal of the IR. So you can so that if you detect the output, it's going to be a voltage output changing periodically depends on your heart flow. Because whenever your heart pumps blood into a finger, there will be a lot of blood, and with so of course more oxygen in there. So you are getting different oxygen levels in your fingertip. So you are getting different voltage outputs. And you can amplify it using different stages, and eventually receive this on the oscilloscope. And you can even use a Arduino to show these heartbeats. And if you do a peak detector, you can find out your heart beat rate just with a super simple filter amplifier circuit in the lab. It just takes like a few hours, 2 hours, you can build it. And so if I teach it again, you are going to take it next time, so you'll get a chance to do this. All right. See you on Monday next week.